Hello class, welcome to the final segment in the week 4 material, and in this final segment we're going to take what we did in the previous segment, the application side of things, and add a circle to the mix, and then also ask if a particular point in question lies both within the rectangle, if both lies within the rectangle and the circle that is centered in the rectangle itself. So here we're going to walk through the logic behind that and see how that ties into the realm of Boolean logic. So a lot of this stuff is going to be the same, but since we're adding a circle, we're of course going to be adding more information to a Python program to sort of answer this question. And again, the question this time we're trying to ask is if any point x, y lies both within the square in question and also lies within a circle that is centered in the square. So one thing that might be helpful to start off with is to get sort of more of a visual standpoint of what exactly is going on here. So this is the same thing that we left off with. So again, this square given by these particular bounds, the same exact thing and the same exact point that we're testing. And if we want to get an idea of what sort of result we should expect for this particular value of x and y, we can throw a circle into that square. And again, this circle is going to be centered. The center of that circle is also going to be centered at the center point of the square. And from a visual inspection, we can see that we do in fact expect the computer to say the answer to that question is yes. This particular point, x equals 15, y equals 15, lies within the square, and it also is contained within the circle. So right off the bat, we get an idea of what the computer should tell us as a final result if our logic or if our computer is in fact, or if our program is in fact working correctly. I almost said computer working correctly, but we also hope that is the case as well. So one of the first things that we're going to have to do is we're going to have to take the leftmost extent, the rightmost extent, the topmost extent, the bottommost extent of our square in question, and first figure out where the center point is. So that's just going to make use of the midpoint formula from geometry. So if you want to find the midpoint between any combination of points, then you simply add up all the points in question and then divide by the total. So if we want to find the midpoint for our square, that is the center of our square, then we take the two x values in question, which are represented as a and b, add those together, divide by 2, and that will tell us the center of our square, the x coordinate for the center of our square. And if we do the same thing for the y coordinate, this time with c and d, add those up, divide by 2, that will tell us the y coordinate for the center of our square. So if we were to do this calculation, we would get 10 plus 30 divided by 2, which is 20. And then we would get the same exact result since C is equal to A and D is equal to B. So we would get 10 plus 30, which is 40, divided by 2 is 20. So the center of our square is going to be at the coordinates 20, 20, which if we go back to our diagram, that makes sense. If we look at 20, 20, that's where this mouse cursor, as you can see, that is in fact at the center of our square in question here. And if you want to ask if a particular point is contained within the circle, the question is actually a lot simpler than it is for, say, a square. And the reason why is it has to do with the definition of a circle itself. So the most fundamental geometric definition of a circle is you take a distance from some point and you trace out a curve, and at every point along that curve is the same distance from the center of the circle in this case. So sort of representing that here, at every point along the edge of the circle, every point there is the same distance away from the center of the circle. That is itself the most fundamental definition of a circle, and we can use that definition to ask the question if a particular point is contained within the circle. And the way we do that is, since every point along the circle is the same distance away from the center, then the only thing we really need to ask is, our point in question, what is the distance from our point in question to the center of the circle? So in this case, the distance from this point 15, 15 to the center of the circle, what number is that? And then we simply take that number and ask, is that number less than the circle's radius? Because again, the radius, that is the distance that you get to every single point along the edge of the circle here. So for every point along the edge of the circle is the same distance from the center of the circle. Again, that's the fundamental geometric definition, and that distance itself is called the radius. So if we take a point in question, calculate its distance from the center of the circle, we get a number from that, and then we then ask if that particular number is smaller than the circle's radius, and if it is, then that particular point is in fact contained within the circle. Otherwise, say a point way out here, that distance from the circle center is larger than the radius, so that point where the mouse cursor is not contained within the circle. So that's just the question asking if our point is contained within the circle, but we also want to ask the question if this point is also contained within the square. So we actually kind of said the word already, what we're going to actually be doing here. So we want to first ask the question, is our point contained within the square? And we also want to know if that is true, and very important three-letter word there. And we also want to know if our point is contained within the circle. So we first need to ask the question, is our point contained within the square? Then we need to ask the question, is our point contained within the circle? And if the answer to both of those things is true, then we would then conclude our point lies within both the square and the circle. And if we want to take a look at what this looks like in our Python program, so here, there's some interesting stuff going on here on line 15, but the main thing that you want to know is that this is calculating the distance from our point to the center of the circle. So this is one component of that important question that we're trying to ask. In our point in question, x is x15, y equals 15, we want to know how far away that particular point is from the center of the circle. And this here on line 15 is just using the distance formula to calculate the distance of x, the distance that our point xy is from the center of the circle. So that's just an application of the distance formula and this math.square root here, which we'll talk about a little bit later on, that allows us to calculate the square root of a number. So this is sort of an extension of the Pythagorean theorem. The difference in the x-coordinates squared plus the difference in the y-coordinates squared, you take the square root of that and you then calculate the distance from the two ordered pairs in question. In this case, our test point x comma y, and the other ordered pair in question is the circle, the center of the circle's x-coordinate and the center of the circle's y-coordinate. And the other piece of information that we need is the radius of the circle. So if this is the diameter of the circle, since the circle is centered in the square, if this is the diameter, going from x equals 10 to x equals 30, if that's the diameter, then the radius is just half that difference. So I just simply take 30 minus 10 to get 20. That's the diameter of the circle. Just take a minute to convince yourself of that. And if we take that number and divide it by 2, that'll give us the radius of the circle, which is the other important piece of information that we're after. And that's the calculation that we do here. We could have also done this with the y-coordinate since we have a square, but either one is going to work. In this case, I just chose to use the x-coordinate because those are the first two variables that appear up here. But you could also do the same calculation with the y values given by c and d. So we take the difference, the rightmost extent minus the leftmost extent, get that number, which is the diameter. Again, we verified that using the diagram. Then we half that value to get the radius. And now, the question that we're really after is the distance from our point to the circle center, represented by this variable, which we calculate on line 15. Is that value less than or equal to the circle radius, which we calculate on line 17? So that alone, this entire thing right here is just simply asking the question, is our point contained within the circle? And then this entire thing enclosed in this set of parentheses is asking the question, is our point contained within the square? And if both those things are true, again enforced by this AND operator between the two conditions in question, am I contained within the square? And am I contained within the square? Or am I contained within the square and am I contained within the circle? And if both those things are true, then this entire smorgasbord of a condition is true, which means the computer will run this print statement printing out the point xy lies within the square ABCD and within the circle that is centered in the square. And from a visual inspection, we can see that our point 1515 should satisfy both those conditions. It should be contained within the square, and it should also be contained within the circle. So if our logic here checks out and our program is set up correctly, then we should get this exact result when we go to run this program, and you can see it does in fact tell us the point XY lies within the square ABCD and within the circle that is centered in the square. But that's going to do it for this final segment of the week 4 material. And again, if you might want to make sure you fully understand this, it might be helpful to go back through this segment to make sure you understand the logic behind all the geometry and everything that we talked about. But other than that, that's all I have for the week 4 unit. And again, this is just one of many potential applications of Boolean logic. We will discover many more applications as we progress through the semester, but this is just sort of a first look at something that is relatively easy to explain because it's geometry related, which is really easy to represent visually. But that's going to do it for the week 4 unit. So with that, I will see you all in the next week's unit.